Section 1 Introduction. We're excited to discuss recent advancements in the field of text-to-image (T2I) personalization, which have paved the way for innovative applications. Specifically, we're focusing on face personalization, which enables the creation of new images of a specific person's face in various styles. This wide range of styles is made possible by the robust pre-existing knowledge of a pre-trained diffusion model. A notable example of this is DreamBooth, which can incorporate a new subject into the model without disrupting its existing knowledge. One of the key features of this method is its ability to retain the unique characteristics and details of the subject, even when applying drastically different styles. For instance, if we train the model using photos of a person's face, we can generate new images of that person in animated cartoon styles. The resulting cartoon figure will still retain some of the person's unique features, indicating that the diffusion model has some level of visual semantic understanding. However, despite its impressive capabilities, DreamBooth has a few drawbacks, namely its size and speed. The original DreamBooth paper describes a process that fine-tunes all the weights of the UNet and text encoder of the diffusion model, resulting in a size of over 1 GB for stable diffusion. Additionally, training a DreamBooth model takes about 5 minutes for stable diffusion, which involves 1,000 iterations of training. These limitations restrict the potential impact of the work. In this paper, we aim to address these issues without compromising the key features of DreamBooth, such as its diverse style range and subject fidelity. We propose a solution that maintains the integrity of the model and accurately captures the essence of the subject in a quick and efficient manner with a smaller model. Our proposed solution, Lightweight DreamBooth, LIDB, is a personalized text-to-image model that only requires about 100 kilobytes for the customized part. This is achieved by training a DreamBooth model in a low-dimensional weight space created by a random orthogonal incomplete basis within a low-rank adaptation weight space. We also introduce a new HyperNetwork architecture that utilizes the lightweight DreamBooth configuration and generates the customized part of the weights for a given subject in a text-to-image diffusion model. This provides a strong initial direction that allows us to further fine-tune the model to achieve high subject fidelity within a few iterations. Our method is 25 times faster than DreamBooth while delivering similar results. Additionally, we propose a technique called rank-relaxed fine-tuning. This involves relaxing the rank of a LoRa DreamBooth model during optimization to achieve higher subject fidelity. This allows us to start the personalized model with an initial approximation using our HyperNetwork, and then approximate the high-level subject details using rank-relaxed fine-tuning. One of the key insights that led us to explore a HyperNetwork approach is the understanding that to synthesize specific subjects with high fidelity using a given generative model, we need to alter its output domain and incorporate knowledge about the subject into the model, specifically by modifying the network weights. Section Summary. Recent advancements in text-to-image personalization have allowed for the generation of new images of specific faces or individuals in different styles. However, existing methods like DreamBooth suffer from issues of large size and slow speed. In this work, we propose Lightweight DreamBooth, LIDB, a personalized text-to-image model that addresses these shortcomings by training a low-dimensional weight space model and leveraging a new HyperNetwork architecture. Our approach achieves similar performance to DreamBooth but is 25 times faster, making it more practical for real-world applications. Section 2 Related Work. In this section, we'll discuss related work in the field of text-to-image (T2I) models and personalization of generative models. Firstly, let's talk about text-to-image models. There are several recent models, including Imagine, DALL-E2, Stable Diffusion, SD, Muse, Party, and others, that have shown impressive capabilities in generating images from text prompts. Some of these models, like Stable Diffusion and Muse, even allow for the generation to be influenced by a given image through an encoder network. Techniques like ControlNet have proposed ways to include new input conditions, such as depth. However, these models often fail to capture enough detail about the subject. For our experiments, we've chosen to use the Stable Diffusion model due to its smaller size. However, our proposed technique can be applied to any T2I model. Next, let's discuss the personalization of generative models. The goal here is to generate images of a specific subject in various contexts, given one or a few images of that subject. Earlier work in this area used GANs to edit a given subject image into new contexts. Techniques like pivotal tuning suggested fine-tuning a GAN with an inverted latent code. Other researchers proposed fine-tuning style GAN with about 100 face images to get a personalized generative prior. Some suggested conditioning a GAN with an input image to generate variations of that image. However, all these GAN-based techniques either resulted in poor subject fidelity or lacked diversity in the generated image's context. HyperNetworks were introduced as a way to use an auxiliary neural network to predict network weights, thereby altering the functioning of a specific neural network. They have since been used for image generation tasks related to personalization, such as inversion for style GAN, which is similar to work that seeks to invert an image's latent code to edit that image in the GAN latent space. More recently, several works have proposed techniques for personalizing T2I models, resulting in higher subject fidelity and versatile text-based recontextualization of a given subject. For instance, textual inversion suggests optimizing an input text embedding based on a few subject images and using that optimized text embedding to generate subject images. Other researchers have proposed a more detailed textual inversion space. DreamBooth suggests optimizing the entire T2I network weights to adapt to a given subject, resulting in higher subject fidelity in the output images. Several works propose ways to optimize compact weight spaces instead of the entire network, as in DreamBooth. For example, custom diffusion suggests optimizing only the cross-attention layers, SVDiff suggests optimizing the singular values of weights, and LoRa suggests optimizing low-rank approximations of weight residuals. StyleDrop proposes using adapter tuning and fine-tuning a small set of adapter weights for style personalization. DreamArtist proposes a one-shot personalization technique using a positive-negative prompt tuning strategy. Despite generating high-quality subject-driven generations, most of these fine-tuning techniques are slow and can take several minutes for every subject. Section summary. Several recent models, such as Imagine, DALL-E2, Stable Diffusion, SD, Muse, and Party, have demonstrated excellent image generation capabilities given a text prompt. However, existing text-to-image models do not capture sufficient subject details. Personalization of generative models has been explored using techniques like GANs and HyperNetworks, but they suffer from poor subject fidelity or lack of context diversity. Recent works propose techniques for personalizing text-to-image models resulting in higher subject fidelity and versatile recontextualization, but most of these techniques are slow and time-consuming. Section. Fast T2I personalization. We're going to discuss the rapid personalization of text-to-image, T2I, models. Several contemporary studies have suggested different methods to speed up this process. Some researchers suggest using encoders to predict initial text embeddings, followed by fine-tuning the entire network to improve the accuracy of the subject. However, our approach is different. We use a hypernetwork that directly predicts low-rank network residuals. SUDI, another method, starts by creating a large dataset of input images and their corresponding recontextualized images, which are generated using the standard DreamBooth. This dataset is then used to train a separate network capable of generating personalized images in a feed-forward manner. While this method reduces the need for fine-tuning, it has its drawbacks. The inference model in SUDI doesn't maintain the original T2I model's integrity and often lacks high subject accuracy. Instant Booth and Taming Encoder introduce a new conditioning branch for the diffusion model. This branch can be conditioned using a small set of images, or even a single image, to generate personalized outputs in various styles. However, to achieve this, both methods require training either the diffusion model or the conditioning branch. They are trained on large image datasets, with Instant Booth using 1.3 million samples of bodies from a proprietary dataset, and Taming Encoder using Celeba and Getty. Fast Composer suggests using an image encoder to predict subject-specific embeddings, focusing on the issue of identity blending in multi-subject generation. Some researchers propose guiding the diffusion process using face recognition loss to generate specific subject images. However, these guidance techniques often struggle to balance diversity in recontextualizations and subject accuracy, while also keeping the generations within the image distribution. Face Zero suggests conditioning a T2I model on face embeddings, allowing for the generation of subject-specific images in a feed-forward manner without any test time optimization. Celeb Basis suggests learning the PCA basis of celebrity name embeddings, which can then be used for efficient personalization of T2I models. In contrast to these existing techniques, we propose a unique approach based on hypernetworks. Our method directly predicts low-rank network residuals for a given subject. Section summary. Several methods have been proposed for faster personalization of T2I models. Some approaches involve learning encoders to predict initial text embeddings and then fine-tuning the complete network, while others use separate networks trained on paired datasets for personalized image generation. Our approach, however, directly predicts low-rank network residuals using a hypernetwork, which offers a unique and efficient way to personalize T2I models. Section 3 Preliminaries. In this section, we'll be discussing the basics of latent diffusion models, LDM, and how they're used in text-to-image, T2I, diffusion models. These models work by gradually removing noise from a noise map to create an image that matches a given text prompt. The text prompt is transformed into an input text embedding using a text encoder. In our research, we specifically use Stable Diffusion, a type of LDM. LDMs are made up of three main parts: an image encoder that turns an image into a latent code, a decoder that turns the latent code back into image pixels, and a U-Net denoising network that gradually removes noise from the latent code. Our tool, DreamBooth, uses a strategy to fine-tune a given T2I denoising network to generate images of a specific subject. It does this by optimizing all the weights of the diffusion network based on a few given subject images, while also maintaining the original model's ability to generalize with a class-specific prior preservation loss. In the case of Stable Diffusion, this means fine-tuning the entire denoising U-Net, which has over 1 GB of parameters. DreamBooth can work on a single subject in about 5 minutes with 1K training iterations. We also use a technique called low-rank adaptation, LoRa, to make DreamBooth more memory efficient and faster. Instead of fine-tuning the entire network weights, LoRa fine-tunes the weight residuals. This is typically applied to the cross and self-attention layers of the network. A key feature of LoRa is that it breaks down the residual weight matrix into low-rank matrices. This is beneficial because the combined number of weights in both matrices is much lower than the number of parameters in the original residual. Previous research has shown that this low-rank residual fine-tuning is an effective technique that maintains several favorable properties of the original DreamBooth while also being memory efficient and fast, even when we set the rank to 1. For the Stable Diffusion 1.5 model, LoRa DreamBooth with a rank of 1 has approximately 386K parameters, which is only about 1.6 megabytes in size. Section Summary. In this section, the authors introduce latent diffusion models, LDM, for text-to-image, T2I, generation. They explain that LDM consists of an image encoder, a decoder, and a U-Net denoising network. They also present DreamBooth, a fine-tuning strategy for T2I denoising networks, which optimizes the network weights on specific subject images while preserving the generalization ability. Additionally, they propose low-rank adaptation, LoRa, as a memory-efficient and faster technique for DreamBooth, where the network weight residuals are fine-tuned instead of the entire weights. The key idea of LoRa is to decompose the weight residuals into low-rank matrices, which significantly reduces the number of parameters. Section 4 Method. In this section, we'll explain our method, which is built on 3 main components. First, we'll introduce the lightweight DreamBooth, LIDB, concept and show how we can further break down the low-rank decomposition, LoRa, of the weights to reduce the number of personalized weights in the model. Then, we'll talk about the HyperNetwork training and the model architecture that allows us to predict the LIDB weights from a single image. Finally, we'll discuss rank-relaxed fast fine-tuning, a technique that significantly improves the quality of the output subject in just a few seconds. We'll also provide an overview of the HyperNetwork training and fast fine-tuning strategy used in our HyperDreamBooth technique. The lightweight DreamBooth, LIDB, is designed with the goal of creating a personalized subset of weights directly using a HyperNetwork, while keeping the number of these weights as low as possible without compromising the quality of the subject, its editability, and style diversity. We propose a new low-dimensional weight space for model personalization that allows for personalized diffusion models that are 10,000 times smaller than a DreamBooth model and more than 10 times smaller than a LoRa DreamBooth model. Our final version has only 30,000 variables and requires just 120 kilobytes of storage space. The key idea behind LIDB is to further break down the weight space of rank 1 LoRa residuals. We do this using a random orthogonal incomplete basis within the rank 1 LoRa weight space. This can be visualized in the provided figure. In more straightforward terms, we further break down the down, A, and up, B, matrices of LoRa into 2 matrices each. We denote these as A equals A underscore aux A underscore train and B equals B underscore train B underscore aux, where the aux layers are randomly initialized with row-wise orthogonal vectors and are kept constant, while the train layers are learned. We introduce 2 new hyperparameters, A and B, which we determine through experimentation. The weight residual in a LIDB linear layer is represented as delta Wx equals A underscore aux A underscore train B underscore aux. Here, R is much smaller than the minimum of N and M, A is less than N, and B is less than M. A underscore aux and B underscore aux are randomly initialized with orthogonal row vectors of constant magnitude and kept constant, while B underscore train and A underscore train are learnable. Interestingly, we find that with A equals 100 and B equals 50, which results in models that have only 30,000 trainable variables and are 120 kilobytes in size, the personalization results are strong and maintain subject fidelity, editability, and style diversity. We'll show the results for personalization using LIDB in the experiment section. Section Summary. The method proposed in this section consists of three core elements: the lightweight DreamBooth, LIDB, HyperNetwork training, and rank relaxed fast fine-tuning. LIDB reduces the number of personalized weights in the model while maintaining strong results for subject fidelity, editability, and style diversity. By decomposing the weight space of a rank 1 low rank decomposition, LIDB achieves personalized diffusion models that are significantly smaller in size, with only 30K variables and 120 kilobytes of storage space. Section 4.2 HyperNetwork for fast personalization of text-to-image models. We're introducing a HyperNetwork to quickly customize a pre-existing text-to-image (T2I) model. This HyperNetwork, denoted as H with ADA parameters, uses an image as input and predicts the LIDB low-rank residuals. These residuals are represented by a symbol that looks like theta with a hat on top, and they are derived from a set of matrices, represented by tilde theta, which are associated with the cross-attention and self-attention layers of the T2I model. The HyperNetwork is trained using a collection of images specific to a certain domain. The training process involves two types of loss: a basic diffusion denoising loss and a weight space loss. The first loss measures the difference between the reference image and the noisy image processed by the diffusion model, while the second loss measures the difference between the predicted residuals and the pre-optimized weight parameters of the personalized model for the reference image. The relative importance of these two losses is controlled by two hyperparameters, alpha and beta. We're also proposing a new approach to the supervisory text prompt. Instead of using a learned token embedding, we're suggesting that the HyperNetwork should only predict the LIDB weights of the diffusion model. The learning process is conditioned on a phrase like A, V, face, where V is a unique identifier. At the time of inference, this prompt can be modified to include semantic changes, such as A, V, face in impressionist style. The architecture of the HyperNetwork is divided into two parts: a VIT image encoder and a transformer decoder. We're using a VIT H for the encoder and a 2 hidden layer transformer decoder for the decoder. The transformer decoder is particularly suitable for this weight prediction task because the output of a diffusion UNet or text encoder depends sequentially on the weights of the layers. This means that to personalize a model, the weights from different layers are interdependent. In previous work, this dependency wasn't rigorously modeled in the HyperNetwork. However, with a transformer decoder that includes a positional embedding, this positional dependency is modeled, much like the dependencies between words in a language model transformer. To our knowledge, this is the first time a transformer decoder has been used as a HyperNetwork. Section Summary. The authors propose a HyperNetwork that enables fast personalization of a pre-trained text-to-image (T2I) model. The HyperNetwork takes an input image and predicts the low-rank residuals of the T2I model. It is trained on domain-specific images using a diffusion denoising loss and a weight space loss. The HyperNetwork architecture consists of a VIT image encoder and a transformer decoder, which effectively models the interdependence of weights from different layers. Section: Iterative Prediction. We've discovered that our HyperNetwork performs better and makes more confident predictions in an iterative learning and prediction scenario. In this scenario, we feed initial weight predictions to the HyperNetwork, and its job is to enhance these initial predictions. We only encode the image once, and the features we extract from this process are used for all rounds of iterative prediction by the HyperNetwork's decoding transformer. This method speeds up both training and inference, and we found that it doesn't compromise the quality of the results. To explain this in simpler terms, the forward pass of the decoding transformer can be described as follows. The predicted weight at the current iteration, let's call it K, is a function of the extracted features and the predicted weight from the previous iteration, K1. This process continues until we reach a predetermined maximum number of iterations, which we'll call S. We start the process with the weights initialized to 0. We then use trainable linear layers to convert the decoder outputs into the final layer weights. We trained our HyperNetwork using the Celeb AHQ dataset and found that we only needed 15,000 identities to get strong results. This is significantly less data than what other similar methods require. We also found that the initial HyperNetwork prediction is largely accurate in terms of direction and consistently generates faces with similar attributes, like gender, facial hair color, skin color, etc., to the target face. However, it doesn't capture fine details as well. To address this, we propose a final fast fine-tuning step that captures these details. This step is much faster than the method used by DreamBooth, but it achieves virtually identical results with strong subject fidelity, editability, and style diversity. In this step, we first predict personalized diffusion model weights and then fine-tune these weights using the diffusion denoising loss. A significant contribution of our work is the concept of rank-relaxed fine-tuning. Here, we relax the rank of the LoRa model from 1 to a number greater than 1 before fast fine-tuning. We add the predicted HyperNetwork weights to the overall weights of the model, and then perform LoRa fine-tuning with a new higher rank. This approach enhances our method's ability to approximate high-frequency details of the subject, resulting in higher subject fidelity than methods that stick to lower ranks of weight updates. As far as we know, we're the first to propose such rank-relaxed LoRa models. We use the same supervision text prompt, A-V, face, for this fast fine-tuning step. We found that, given the HyperNetwork initialization, fast fine-tuning can be done in 40 iterations, which is 25 times faster than DreamBooth and LoRa DreamBooth. We provide an example of initial, intermediate, and final results in the figure. Section summary. The HyperNetwork achieves better predictions through iterative learning and prediction, using intermediate weight predictions to improve the initial prediction. By performing image encoding once and using the extracted features for all rounds of iterative prediction, training and inference are sped up without affecting the quality of results. Additionally, a rank-relaxed fast fine-tuning step captures fine details, achieving virtually identical results to DreamBooth with strong subject fidelity, editability, and style diversity, but in a much faster manner. Section 5 Experiments. We've developed our HyperDreamBooth using the Stable Diffusion version 1.5 diffusion model. This model predicts the LoRa weights for all the layers of cross and self-attention in the diffusion UNet, as well as the clip text encoder. For the sake of privacy, we've used synthetic face images from the SFHQ dataset for our visuals. For training, we've used 15,000 images from the Celeba HQ dataset. Our method has shown impressive results in personalizing a wide range of faces, matching or even surpassing the performance of the best optimization-driven methods currently available. Furthermore, our method offers excellent editability, allowing us to transform face identities into vastly different domains like figurines and animated characters. We've also managed to maintain the strong style prior of the model, which enables a broad range of style generations. We've included some results in a figure. However, due to the statistical nature of HyperNetwork prediction, there can be some samples that are out of distribution, OOD, for the HyperNetwork due to factors like lighting or pose, which can lead to less than optimal results. We've identified 3 types of errors that can occur. 1. A semantic directional error in the initial prediction of the HyperNetwork, which can result in incorrect semantic information about a subject, like wrong eye color, hair type, or gender. 2. Incorrect capture of subject detail during the fast fine-tuning phase, which can produce samples that are close to the reference identity but not similar enough. And 3. Underfitting of both the HyperNetwork and fast fine-tuning, which can result in low editability with respect to some styles. We've compared our method to both textual inversion and DreamBooth using the parameters proposed in both works. The only difference is that we've increased the number of iterations of DreamBooth to 1,200 to improve personalization and facial details. The results, shown in a figure, indicate that our method generally outperforms both textual inversion and DreamBooth in the one-input image regime. Section summary. The authors implemented their HyperDreamBooth on the Stable Diffusion version 1.5 diffusion model and predicted LoRa weights for various layers of the diffusion UNet and the clip text encoder. They achieved strong personalization results for diverse faces, with performance surpassing state-of-the-art methods. They also demonstrated the ability to transform face identities into different domains while maintaining the model's style prior. However, they noted that errors can occur due to the statistical nature of HyperNetwork prediction, such as semantic directional errors, incorrect subject detail capture, and underfitting. They compared their method to textual inversion and DreamBooth, showing that their method generally outperforms both in the one-input image regime. Section. Quantitative comparisons and ablations. We've conducted a detailed comparison and analysis of our method against textual inversion and DreamBooth. We used a face recognition metric, which is based on an Inception ResNet model trained on the VGG Face2 dataset, as well as the Dino, Clip-I, and Clip-T metrics. Our test involved 100 identities from the Celeb AHQ dataset and 30 prompts, which included both simple and complex style modification and recontextualization prompts. This resulted in a total of 30,000 samples. Our results, as shown in the table, indicate that our method outperforms the others across all metrics. However, it's important to note that face recognition metrics may not be as effective in this particular scenario. This is because these networks are trained only on real images and may struggle to recognize the same person in different styles. To address this, we conducted a user study, which we'll discuss in more detail later. We also compared our method to a more aggressive version of DreamBooth training, which involved fewer iterations and a higher learning rate. Specifically, we used 400 iterations for DreamBooth AG1 and 40 iterations for DreamBooth AGG2, compared to 1200 for the standard DreamBooth. We adjusted the learning rate and weight decay to compensate for the reduced number of iterations. It's worth noting that DreamBooth AGG2 is roughly equivalent to only doing fast fine-tuning without the HyperNetwork component of our work. Our results, shown in the table, indicate that more aggressive training of DreamBooth generally leads to poorer results unless our method is used, which includes a HyperNetwork initialization of the diffusion model weights. We also conducted an ablation study of our method. We tested our method without the HyperNetwork, no Hyper, with only the HyperNetwork without fine-tuning, only Hyper, and with our full setup but without iterative HyperNetwork predictions, k=1. Our results, shown in the table, suggest that our full setup with iterative prediction provides the best subject fidelity, albeit with a slightly lower prompt following metric. In our user study, we evaluated face identity preservation of outputs and compared our method to DreamBooth and textual inversion. We showed the users a reference face image and 2 random generations using the same prompt from our method and the baseline. We then asked the users to rate which one most closely resembled the reference face image. We tested a total of 25 identities and asked 5 users per question, resulting in a total of 1,000 sample pairs evaluated. We used majority voting for each pair. Our results, shown in the table, indicate a strong preference for our method in terms of face identity preservation. Section summary. In this section, the authors compare their method to textual inversion and DreamBooth using various face recognition metrics. They find that their approach achieves the highest scores in all metrics. They also conduct an ablation study and show that their full setup with iterative prediction achieves the best subject fidelity. Additionally, they conduct a user study and find a strong preference for face identity preservation in their method compared to DreamBooth and textual inversion. Section 6. Societal impact. 6. Impact on society. Our goal with this work is to provide users with a tool that enhances their creativity and self-expression in a user-friendly way. However, we acknowledge that sophisticated image generation techniques can have multifaceted societal implications. The method we propose shares many potential issues common to this type of image generation, such as the modification of sensitive personal attributes like skin color, age, and gender, and the potential to perpetuate existing biases present in the training data of pre-trained models. The open-source pre-trained model we utilized, known as Stable Diffusion, is not exempt from these issues. These concerns are not new and have been discussed in numerous recent studies on personalization. The only additional risk our method poses is its increased efficiency and speed compared to previous methods. In our tests, we didn't observe any new issues related to bias or harmful content compared to previous studies. We also found that our method performs equally well across various ethnicities, ages, and other significant personal characteristics. Despite these findings, it's crucial for future research in generative modeling and model personalization to continue examining and addressing these concerns. Section summary. This work aims to provide users with a tool to enhance their creativity and self-expression through intuitive image creation. However, advanced image generation methods can have complex societal impacts, including the potential to alter sensitive personal characteristics and reproduce unfair biases. While our proposed method addresses some of these concerns, further research is needed to validate and address potential risks related to bias and harmful content.